Okay, now this problem, this is still less than 2.5, and we want to find the limit of the sequence, then define it. So this is similar to what you're going to see on the homework. And so we have here a to the n is equal to 2n over n plus 1, where the sum of n equals 1 to infinity for a to the n. So that produces the limit as n approaches infinity for 2n over n plus 1. And since the degree of the numerator is the same as the degree of the denominator, then the limit is going to be the coefficient of your highest degree terms, which is going to be 2 over 1. So our limit is 2. If the degree of the numerator was less than the degree of the denominator, then your degree would be 0. If it's larger, then you have no limit. So from here, we can state for all epsilon greater than 0, there exists a boundary n greater than 0 such that our sequence n is greater than our boundary n. And so then we have here our sequence a sub n minus its limit is less than epsilon. So once we prove that, then we can say that the limit of 2n over n plus 1 equals 2 exists. So when we talk about defining it, we're talking about proving it. So we're going through the proof here. But before we do that, we have to go through the scratch work, and then we can go back and define our proof. So we start with our absolute value of our sequence minus its limits less than epsilon. So the sequence a to the n, we said, is 2n over n plus 1. So this will be 2n over n plus 1 minus the limit, which is 2. And that's less than epsilon. So what we're trying to do here is we're trying to, once we solve for n, then we can define our boundary, uppercase n, and then we can go ahead and define our proof and work it out from there, and then work backwards from that to show our proof. So from here, we need a common denominator. So that's going to be 2n over n plus 1 minus 2 times n plus 1 over n plus 1. Because n plus 1 over n plus 1 is 1. And that's less than epsilon. So now we have to distribute that 2, and we can combine under one denominator. So that'd be 2n minus 2n. And so this would be 2 times n, negative 2 times n, that'd be negative 2n. And negative 2 times 1, that'd be negative 2 over 1 common denominator of n plus 1. And that's all less than epsilon. Well, we have 2n minus 2n. That's just, that all goes to 0. So we're left with the absolute value of a negative 2 over n plus 1 is less than epsilon. All right, so hopefully you're beginning to see a pattern here of how this works. So since we have an absolute value, we're always going to get a positive result, so we can drop the negative. And so that'll just be 2 over n plus 1 is less than epsilon. And from there, because it's always positive, we can drop the absolute value, and so that'll be 2 over n plus 1. Since n is always positive as well, as you know, you're going to have positive, so that'll be 2 over n plus 1 is less than epsilon. So now we need to solve for n. So we're going to apply plus, we're going to multiply n plus 1 to both sides. N plus 1. And so the n plus 1's cancel, and we get 2 is less than epsilon times n plus 1. So now we can divide. We're still trying to solve for n here, so we got to divide epsilon to both sides. And so we get here 2 over epsilon is less than n plus 1. So now we apply minus 1 to both sides. Minus 1, minus 1. And so we get 2 over epsilon minus 1 is less than n. So that's the same thing as if we flipped it as n. N is on the larger end, so n is going to be on the larger end here. 2 over epsilon minus 1. Okay, so you may be wondering, well, why last time did we change this n plus 1 in the previous problem to just 1 over n? Well, I wanted to show you this way to show just the difference. So you could have done it this way on the previous problem, and improve that. But I just wanted to show you a different way of doing this. All right, so from here, we can go ahead and write our proof and then work backwards. So now, since our sequence n is greater than our boundary n, then we can say that our boundary n is greater than 2 over epsilon minus 1. Because the boundary n is smaller than the sequence n, so boundary n can be also larger than 2 over epsilon minus 1. Okay, so now we've found our n. That's what we were trying to find way back in the beginning. Here, we found it. Okay, so from here, we can go ahead and write our proof. And so we would state here that our proof, we can say that we can let all epsilon greater than 0, we choose a n equal to 2 over epsilon minus 1. Then for all sequence n greater than our boundary n, we have our absolute value, our a to the n, our sequence, minus our limit is less than epsilon. So basically, we're going to, from here, we can say that since our sequence n is larger than our boundary n, then we can say that n is greater than our 2, and boundary n is 2 over epsilon minus 1. We can say that our sequence n is greater than 2 over epsilon minus 1. So now we're in the process of working backwards. So we're at this point now, and so we're working backwards from there. So now what we want to do is solve for epsilon. And so we're going to apply +1 to both sides. +1. And so this will be n+1 is greater than 2 over epsilon. Okay, so now we're going to multiply epsilon to both sides. So the whole idea here is eventually we're going to get back to this. Once we get to this point here, then we've proven it, that the limit does exist. So the epsilons cancel here, and we've got epsilon times n+1 is greater than 2. And we're solving for epsilon, so now we can divide both sides by n+1, divide by n+1. And so now we have epsilon is greater than 2 over n+1. Well, that's the same thing as if we said 2 over n+1 is less than epsilon. Okay, so we're starting to get closer and closer to working backwards in this sequence, and so eventually we're going to get back up to here. So at this point now we can go ahead and put in our absolute values back in there, because that is the same as our absolute value since it's already positive. And so because we have the absolute value, that's the same thing as if we had a -2 in there over n+1, because it's an absolute value, is less than epsilon. So now we need our n. So since we had here 2 n's, right? So now we have to add and subtract 2 n's. So this will be -2 plus 2n minus 2n over n+1, and that's less than epsilon. Because this is the same thing as if we just said -2, right? And since we needed a 2, we had to factor that 2 out. So now we can switch places with this 2n and the -2. So that'll be 2n minus 2 minus 2n all over n+1 is less than epsilon. So from here we can factor out the negative, so that's 2n minus, and then factor out a -2. So that leaves us with 1 plus n, right? Or 1 plus n or n+1, either way. And so from here we can split it, and all that is less than epsilon. So now we can split this as 2n over n+1 minus 2 over, and then 1 plus n is the same as n plus 1 over n plus 1 is less than epsilon. And so n plus 1 over n plus 1 is just 1. So this is going to be 2n over n plus 1 minus 2. So we can cancel these two out, and it just leaves with 2 is less than epsilon. And there we go. We've proven it. We've proven it to here. We've proven this to be true. And so since it's proven, that's all there is that you have to do to it. So again, you have to start with the scratch work, plug it in, find what the uppercase N, you have to solve. So basically what you're doing here is you solve for N, and then since N is larger than our boundary N, uppercase N, then you can start that off in your proof, which is here. Okay, so you start with the scratch work, and then once you get that, then you can just work backwards and show your proof. And that's all there is to this video.